All right, so as usual, when you take an amplifier, what you're interested in is voltage gain, input and output resistances. Comparison with common emitter amplifier. This is our default amplifier. This is the first amplifier that we've studied, and we need to compare and look at how a common base compares with common emitter amplifier. We need to look at its frequency response, and we'll see that there's something called a cascade amplifier, which combines the advantages of both common emitter and common base. Okay. All right, so we know this, that the problem that we are trying to address is my upper cutoff frequency falls with gain. Falls sharply with gain, and one of the reasons is the Miller's effect here. Okay, Miller's effect here. This C mu gets multiplied by the gain of the amplifier here. So that's the problem that we are trying to address here. And we said, look for an amplifier with no capacitance between the input and the output, and that is hinting towards a common base amplifier. Okay, where we apply a signal to the emitter and we take it out from the collector as usual. Okay. So if you look at this particular circuit, biasing is exactly the same. I've just turned it 90 degrees. R1, R2, RC, RE, biasing is exactly the same. The only difference is signal is coming from here through the emitter, and we take output again is the same. In common emitter also, we were taking output by putting a coupling capacitor through the collector here. So everything is the same except for two changes. One is signal is being fed here, and the other one is the base is connected to ground through a capacitor here, which means we'll have a small signal ground here. Okay. All right. So DC analysis is straightforward. I don't need to do it. It's the same set of equations. Exactly same. So let's not worry about it. Let's look at mid-frequency analysis here. Mid-frequency meaning all capacitances are ignored. So we have a circuit here. Capacitors are short. Note that the base becomes a short here, ground here. Once you make it ground, what happens is, note that R1, one end is ground, R1, the other end is ground also. So R1 disappears. Similarly, R2 disappears. I don't have any R1, R2 in my circuit here. All I get is the base here becomes ground here. So this is the base part here, which becomes ground here. And so I have R pi. This is my hybrid pi model here. And the signal is being fed Vs and Re here. So you see the signal here on the emitter side here. And on the collector side, RC is there in parallel with RL. So you see it here. So that's the small signal equivalent circuit in the mid-frequency range. It's straightforward to calculate gain. Whatever voltage you apply here between Vs here, you can obviously see the voltage Vs is equal to minus VBE. Note here, the VBE base emitter voltage here is nothing but minus Vs. So what happens is this current source then becomes turned up, and it is equal to GM times Vs. And this current source then flows through RC parallel RL. So you build up gain, which is ICQ RC parallel RL divided by VT. Same gain as a common emitter amplifier. Common emitter was also ICQ RC parallel RL divided by VT. The only difference is phase here. In common emitter, it was minus, which means input and output were 180 degree out of phase. Here, they are in phase with each other. If you have a positive cycle here, you have a positive cycle here. So that's an amplifier in phase. Alright, so same as CE amplifier, but it is non-inverting. Common emitter amplifier was inverting. Alright, input impedance is the impedance that I look from here. I can, as usual, what you will do, input impedance is Vs divided by Is will give you input impedance here. We'll solve it through a different way here. So, input impedance is impedance looking from here. Alright, so impedance looking from here, and remember that this point is ground. So, which will be equal to the impedance looking from here in parallel with Re. Because when I say that impedance looking from here, it is between this node, remember, and ground. And we have seen that if you look into the emitter, what do you see? You see R pi plus any resistance in the base divided by beta. I don't have any resistance in the base. So the resistance when you look into the emitter is R pi by beta. And so Rn then becomes Re here in parallel with R pi by beta. Okay, that's how input resistance comes out. So, and obviously what will happen is typically Re will be much larger than R pi by beta here, and input resistance will be primarily equal to R pi by beta in typical cases here. Short circuit current gain, you can calculate again the current going here and the current going here. I'll leave the calculations. These are simple here. Short circuit current gain is very close to 1. And which we can understand. Current going here is emitter current and the current here is collector current. And the ratio of collector and emitter currents is practically equal to 1. Okay. All right. Now this is interesting. AV is ICQ RC parallel RL. Rn is R pi by beta parallel Re for common base, and R0 equal to RC. R0 I didn't talk about. If you look at resistance looking from here, all you see is RC. Okay, so just as common emitter. Now let's look at these things here. From the first one, I know that AV will be less than ICQ by VT into RC, because RC will always be greater than this factor here. RC is always greater than RC parallel RL, and therefore my gain will always be less than this quantity. Not only that, Rn will always be less than R pi by beta, because Rn is R pi by beta parallel RL. So I have this, and R naught is RC. I can combine these three things together, and we get AV. If you take AV multiplied by Rn, AV by Rn divided by R0 is less than or equal to 1. So that's the constraint that you get for common base amplifier here. AV multiplied by Rn divided by R0 is less than or equal to 1. It will be equal to 1 when my RL is very large. When my RE is very large, then I will get exactly equal to 1. Otherwise, there will be further loss here. So there is a trade-off between gain, input and output resistance. Again, if you want to build up gain, you'll have to sacrifice input resistance. You'll have to either sacrifice R0. But I'm sure you can see the difference between common emitter and common base. In common emitter, the right hand side was beta, and here it is 1. So which one is better? Obviously, you are saying common emitter is better, because you want high voltage gain, high input resistance, and small output resistance here. So you want this quantity to be as large as possible. And here, no matter what beta you have, you can take a transistor with a beta of 200, all you will get is AV Rn by R0 equal to 1. It's not affected by beta here. So what happens is the following. Okay, so this is straight here. If this is 100, this is 1K, you'll get 0.01K. Okay, so for this reason, what people tend, if you read books, you'll find that people say that common base amplifier has a voltage gain which is high. Why? Well, I can build a gain of 100, and I can build an output resistance of 1K, and input resistance then becomes 0.01K. So one way of describing common base amplifier that is very common in books is it can provide you with high voltage gain. It gives you input resistance which is low, and gives you an output resistance which is medium. Which is okay. If I look at these numbers, these are fine. High, low, and medium is fine here. And therefore, when people tend to compare common emitter and common base, they tend to focus on the following. Both provide you with high gain. Common emitter provides you with a medium input resistance. This provides you with a low input resistance here. Both of them provide you with low output impedance here. Okay, medium output resistance here. So this is how usually common emitter and common base are compared with each other, with the emphasis being that common base provides you with a low input resistance here. That's a major problem here. There's nothing wrong except that a more general description or comparison of common emitter and common base is through these two relationships. Common emitter says AV Rn by R0 is less than beta. Common base says AV Rn by R0 is less than or equal to 1. That's a better comparison. And so what you can do is the following. AV, let me say, of common base, Rn of common base, R0 of common base is equal to 1. AV of common emitter, Rn of common emitter, R0 of common emitter is approximately equal to beta. Let me take the ratio of these two. And then I get this here. Okay, I take the ratio of these two, and now it tells you the comparison between the two cases. And there's various comparisons that you can make here. I could do the following. Look at that. I could make the gain same, output resistance of the two same, and then obviously if beta is 100, my Rn of common emitter would be 100 times higher than Rn of common base. So what it's telling you is common emitter amplifier can provide you 100 times larger input resistance as compared to common base for comparable value of gain, comparable value of output resistance. But there are other possibilities also you can see here. What about this one? That also is a possibility. What this says is, for comparable gain, comparable input resistance, a common, did I make a mistake here? Okay, a common base amplifier's output resistance will be larger by a factor of 100. So you can also, there are multiple ways in which you can look upon the two amplifiers. You can say, well, common base amplifier gives me a very low input resistance here. That's the problem. You could also say, common base amplifier gives me a higher output impedance. You can also say that, because for comparable values of gain and input resistance, common base amplifier gives you a higher value of R0. And I'm sure what you can do is the following also. For comparable values of input resistance and output resistance, common base amplifier gives me 100 times smaller gain. So you know, all of these are the same here. So what I'm trying to say is, this picture is limited, is only focusing on one, but we know that there's a trade-off between gain, input, and output resistances, and this is a better way of looking upon the whole thing. That you know, the ratios is equal to beta, and depending on how I look upon it, the common base either suffers in gain, or it suffers in input resistance, or it suffers in output resistance, as compared to common base amplifier. So as a voltage amplifier, it's not very nice, because for a voltage amplifier we require large gain, large input resistance, and a smaller output resistance, and in that it's failing. It's failing in comparison to a common emitter amplifier, right? So as a voltage amplifier, it's not good. I would always prefer a common emitter amplifier. Where the advantages of common base comes in is in frequency response. Okay, so let's come back to this amplifier here, and you know, now I've turned it back to 90 degrees here, so it looks more like a. So in a common emitter amplifier, I was feeding a signal here. In a common base, we are feeding a signal here. So let's look at the frequency response. Lower cutoff frequency is the same. So now what happens is we are going to look under the following cases. In one case, I'm going to assume that my source resistance is negligible. RS is very small. All right. So here is my amplifier, and okay. So I don't have it here. So here is my amplifier here, and now lower cutoff frequency is determined by what? By each one of these capacitors and the resistances that the capacitor sees. Okay. CB, the resistance that the CB sees here, and the resistance that collector capacitance sees here, and the resistance that this one sees here. Now, we know that for comparable values of capacitors, my lower cutoff frequency is determined primarily by this capacitor here, emitter bypass here. Now, if you look at this emitter bypass capacitor, and if I tell you RS is negligible, RS is very small, what is the net impedance that my emitter bypass sees? Is the impedance looking from here, which is nothing but RE in parallel with R pi, and you know, all of that is exactly the same as common emitter. Same thing, you know, is the same capacitance, same resistance that my emitter bypass capacitor sees in a common emitter amplifier. There's no difference. However, if RS is large, then you can see here that CE, in addition to seeing something on this side, also sees a RS here. And therefore, it can offer you a better, a lower cutoff frequency, if RS is large. Okay. But if RS is negligible, there's no gain in terms of lower cutoff frequency. It will remain the same. Okay. Now, a common base amplifier is interesting not so much for lower cutoff frequency, but for upper cutoff frequency. So let's look at the upper cutoff here. All right. So I'll build the model here for upper cutoff frequency. So all the coupling capacitors are shorts. Coupling and bypass capacitors are short. And we have included C pi, C mu. RBB is important. We have included it here. Again, although I've shown it here, we'll neglect the substrate capacitance here. RC is coming in parallel. So that's the picture that we have. Now, if you compare, if you try to recall this picture versus common emitter, what differences do you note with respect to common emitter amplifier? Suppose Vs is not there. You know, when you are talking about frequency response, you can make Vs ground, and then you look at the time constant due to C pi and C mu. So if you compare it with common emitter, what is the difference? In there also I had RBB, RPi, CPi, CMU, GM, R0, RC, RL, everything I had. What is it that I didn't have? Remember what was emitter in common emitter amplifier? It was ground, small signal ground. So this point was small signal ground. While here, at this point, I have an RE and I have an RS connected. Okay, so the only difference that you see if you compare the two circuits are here. I have RE and RS here, and in that case, I didn't have them. Okay, so now, if I ask the question, suppose I'm driving my common base amplifier through a very small value of RS, which means RS is 0, let's say. If RS is 0, then what happens is it becomes ground. It becomes ground here, and then it becomes exactly same as common emitter. Common emitter was exactly like this here. If you go back and look at the equivalent circuit of common emitter, emitter was of course ground. We were feeding in signal from here, and for both cases RS is negligible and VS is short. The two circuits are exactly the same, and they have the same upper cutoff frequency. No difference between common emitter and common base for negligible value of RS. I'll show you. For example, I have a common emitter amplifier and I have a common base amplifier. Note that both are biased in exactly the same manner. Everything is the same if you just look at the two. In one case, signal is being fed here. In the other case, signal is being fed from here. RS is 0 here. RS is 0 here. What do I find? Gains are the same. Input resistance, of course, we see a difference. Output resistance are the same. Upper cutoff frequencies, same. Alright, so we've been saying that common base amplifier will have no Miller's effect, right? Miller's effect, and it will have higher cutoff frequency. We don't see that. We don't see that at all. 5.8 megahertz, 5.8 megahertz. If one is thinking that maybe the numbers are wrong, so one has simulation results. For common emitter and common base, you can't see them apart. I don't know whether you can see a little bit of red here, which means that the two are exactly on top of each other. So, same upper cutoff frequency. So then, the point is that what it is telling you is that if I have negligible RS, then common base doesn't offer you any advantage. Doesn't offer you any advantage. Now, let me show you some interesting result here. In the next case, we put an RS here. RS of 2.2K and RS of 2.2K here. In both of them. Now, note what was the gain earlier? Was 110. And gain of this one has gone down to 30. Why? How am I defining gain? V0 divided by Vs. Why has the gain dropped to 30? Because it has dropped across RS, right? The signal here, part of it got dropped here, and the remaining appeared here, and that got amplified, so the gain dropped to 30. Upper cutoff frequency dropped from what? 5.8 to 1.76. Why did the upper cutoff frequency drop? See, without looking at the calculations and all that, why did the upper cutoff frequency drop here? Well, go back and look at the equivalent circuit. Upper cutoff frequency means what? This is common emitter. When you add an RS, what happens here? There is an RS and then ground. So my CPi, the resistance that my CPi sees will be RBB plus RS here. So my resistance goes up and my cutoff frequency drops. Okay, drops here, 1.76. So that's what we expect about common emitter amplifier. Now, please bear in mind, sometimes we say there's a trade-off between gain and bandwidth. Here, the gain has gone down and the bandwidth has also gone down. Alright? Bandwidth meaning upper cutoff frequency has also gone down and the gain has also gone down. Alright, so don't expect that anytime I reduce the gain, I'll always have increase in bandwidth. That's not true. Okay? Don't expect it in general. So here gain has gone down and frequency is also gone down. Well, look at common base now. Common base also had a gain of earlier 110 or so. Its gain collapsed to 0.48 when I added 2.2K. Less than 1. Why? Why this difference? This is still showing you 30 and this is showing you 0.48. Why this difference? Well, the input impedance of this one is what? Higher. So what happens is the voltage that you apply here, because input impedance is higher, a greater fraction of the voltage goes into the amplifier. The input impedance of this is low. So which means a smaller fraction goes into the amplifier here. Most of them gets dropped here. So it's the difference between the input impedance of these two which is causing your overall gain to drop to such a large value. The input impedance of this amplifier is very, very low. Very low. So when you apply any voltage, almost the entire voltage gets dropped here and nothing goes into the amplifier. And that's why the gain is very small. But interestingly, you see something else. Upper cutoff frequency, look at that. 61 megahertz. Alright, so upper cutoff frequency is really gone up. Right? So what it is showing you is the following. It's pointing out to you something interesting. If I have a common base amplifier and I have a large RS here, then I can get very high upper cutoff frequency here. You're seeing an advantage of common base. But then you may be also wondering, what good is this upper cutoff frequency when I don't have any gain? Right? So that's the issue now. Now we are in a dilemma here that we have an amplifier. If I put a large RS, it gives us a very high bandwidth. Right? But doesn't give us gain. Okay? And here is an amplifier which gives you gain but doesn't give you bandwidth. Okay, so how do we, let's look at this in a little bit more detail here. This one. No. So the idea is that when you put an RS here, under this, so the issue is, why did it go up? First problem. Why did it upper cutoff frequency go up? And one can, through calculation, one can very easily show that it goes up here. If you take a common emitter or a common base, whichever amplifier, if you add an RE here, right? If you add an RE to the emitter, note what happens here. The effective resistance seen by C pi is a little bit of involved calculation. The effective resistance seen by C pi is a large R pi that is here. And the effective resistance seen by C mu is this complicated expression here, R mu. Now, interestingly, what happens is, if RE is 0, you can put here RE0, you find R pi is simply RBB parallel R pi. But if RE goes to infinity, becomes very large, R pi becomes 1 over GM. Okay, now this is important. It's simply coming from calculations right now, but you note what RE is doing. If RE is small, which means 0, my C pi sees what? RBB in parallel with R pi. And RBB in parallel with R pi is what? It's a significant resistance. If RBB is, let's say, 200 ohms, R pi is 2K, at least this value is 200 ohms. When I make RE very large, my calculation shows me that R pi goes to 1 over GM. 1 over GM is how much? 26 ohms. If I bias it at 1 milliampere, it is only 26 ohms. So it's a question of 26 ohms versus, let's say, 200 ohms. So 26 ohms is very small, and therefore the time constant associated with C pi becomes very small. So when you put in an RE here, there are various ways of looking at it. When you put an RE, there's a negative feedback, and that is what is causing it. We'll see in a little bit more detail here. The other one is, when you look at C mu, when you have a C mu, R mu will turn out to be, when you don't have an RE, R mu will turn out to be fairly large. Again, when you put an RE and RE becomes large here, R mu will become fairly small here. So RE is having the effect of reducing the effective resistance seen by C pi and the effective resistance seen with C mu. You can see it here, the two extreme cases here. Look at these two circuits here. In one case, RE is ground. In the other case, RE is open. Compare the effective resistance seen by C pi. What is it here? Resistance seen by C pi is what? RBB parallel R pi, right? Everybody sees that. This is interesting. What is the impedance seen by C pi? It's open. What is the impedance seen by C pi here? What does it see? Do a mental calculation of the impedance. So take C pi out. put a source here, if I put a source here, let's say Vx, if I put a source here Vx, how much is the current flowing here? GmVx. How does this current flow? GmVx flows like this. What? It's flowing down, but where is it, the source here? It starts from here to the ground, goes up like this here. So the way the current is flowing is, the current is flowing like this here. Okay? Now, what impedance does my C pi see then? It of course sees R pi, but in addition to R pi, note that there's a path to the current like this here. So what is the impedance it sees? Can everybody see that the current in this path is GmVx? And what is the voltage across this particular path? Vx. So Vx by GmVx is 1 by Gm. So it sees the following. It sees R pi in parallel with 1 by Gm. And because it is 1 by Gm is much smaller, the effective impedance that I see is only 1 by Gm. And here I see a larger impedance. You can see two extreme cases. When emitter is short and when emitter resistance is very large. You can see the impedance that my C pi sees in the two cases here. And it sees a very small impedance, so time constant is small and frequency response is high. Same thing you can see with respect to C mu. I have C mu with emitter ground and I have C mu with emitter open. Now I'll leave it up to you to see that the impedance that my C mu sees in this case versus this case here. Can you see that one is higher than the other? That the impedance that my C mu sees here is much smaller as compared to impedance seen here. Okay, oh sorry, it's much larger than the impedance seen here. So the message in all of this is the following. When I put a large resistance in my emitter, which is practically amounting to open circuit, I get an upper cutoff frequency which is here. I've already shown you when it is open circuit, impedance seen by C pi is 1 by Gm and impedance seen by C mu is RBB plus RC dash. And I get a very large upper cutoff frequency. And there is no Miller's effect. It doesn't depend on gain. So the point that we are trying to make is the following. If I have a common base amplifier with a large resistance connected between emitter and ground, then I get very high upper cutoff frequency. I don't get any Miller's effect. But the problem is that if you connect a large impedance here, that's what we are saying, a common base amplifier with a large RS, then you don't get any gain. That is the problem here. Okay, so I've shown you again the same thing. Common emitter amplifier, another common emitter amplifier, another common base amplifier here. Don't get bothered about a resistor here. I've just biased it by a current source for a moment here. Okay, I put a current source here for biasing. So what happens is this common base amplifier has a very high cutoff frequency, but practically no gain because almost all voltage is dropping across the 10K resistor here. Nothing is going into the amplifier. This one is giving me some gain, but its upper cutoff frequency is very low. So now this is the trouble that we have about common base here. If RS is 0, its upper cutoff frequency is same as this. If RS is very large, it gives you very high upper cutoff frequency, but no gain. That's where we are. Okay. So the idea is common base then useless? What do I do? Because if I make RS small, then it's really useless because it gives you upper cutoff frequency which is same as this one. And it has lower input impedance and all of that we've already seen. It's of no practical value. Common base has no practical value if RS is 0. If RS is very large, it's potentially useful, but doesn't give you gain. Gain is less than 1. So what do you do then? So you can see here, as a standalone amplifier, common base is, by itself, is not useful. As a standalone amplifier. Now the idea is, can I take common base and connect it to something else? And then it becomes useful. Alone, it's not useful. But as a part of a larger system, can it be useful? Okay. Now this is where, let me see how much time I have. And okay, so I'll not go forward, but I want to point out two kinds of amplifiers here. One is a voltage amplifier. right? Note the input is a voltage, the output is also voltage, which means your interest is in voltages. And in a voltage amplifier, what are you looking for? Input resistance to be very high and output resistance to be low, because you want the signal to go into the amplifier and you want whatever gain you have built up to go to the load. So you want R0 to be 0, Rn to be high. But suppose your signal is not a voltage. Signal is a current. The signal that is coming in is a current, which means what? Signal is a current with a large Rs connected. It's like a current source. And output, you are still interested in voltage. What kind of an amplifier are you looking for now? You're looking for an amplifier. If this is a signal, IS, you want this entire signal to go into the amplifier, right? Signal, you want it to go into the amplifier. What kind of an input resistance do you want? Low input resistance here. You want everything to go into the amplifier here. So here, you are interested in input resistance, which is very low. Is it pointing towards something? That common base amplifier with very low input impedance is ideally suited for current source input. Is suited for a current source input, not for a voltage source input. If I had a current source input, then I could take my common base amplifier and really use it. Because current source input, remember, will come with Rs or what? If it's a very good current source, Rs will be how much? Very large. Which means what? Very large Rs. Which means, you know, if you take your common base, very large Rs here, if you replace it by, so what we are saying is the following. Here, look at this common base amplifier, driven with current source. And Rs is very large. Now maybe I have an amplifier which is useful, right? Earlier, the whole problem was, I was thinking only in terms of voltage. That if I drive in a voltage, I was not getting any gain here, voltage gain. But if I have a current source input, this current source here that you see here will directly go into my amplifier. Will go into my amplifier, will get amplified, and all that we'll see later on. And in addition, because it's a current source, I have a very large resistance connected to the emitter here. And therefore, if I were to examine the characteristics of this amplifier, common base, with current input, I will see a very large bandwidth, and I will see maybe a amplifier which is still very useful. But not as a voltage amplifier. All along we were saying the common base is not very good because we were thinking of it as a voltage amplifier. But if you start thinking of it as a current to voltage, which means input is a current, output is a voltage. Now you'll find it's a very useful amplifier. Okay? All right.